Hey everybody, in this video we're going to talk about the components of a buffer and the buffer function given certain qualifications or certain information, and we're going to basically fill in the rest of the blanks. This should be a good review video simply for what a buffer is. Let's start with that. Any buffer is made of two things. Thing number one is a weak acid, and thing number two is the conjugate base of that weak acid. In this particular scenario, all we've been provided with is that the conjugate base of the buffer is ammonia, NH3. What we've got to come up with is what weak acid would complete that buffer. So really what we have to come up with is what is the conjugate acid of NH3. Remember that the conjugate acid form has one extra H+, and the conjugate base form has one fewer H+. Since the conjugate base is NH3, then I know my conjugate acid has to be NH4 with a +1 charge. We also know that since this is an ion, which can't exist on its own, it's going to have to be added to the buffer in the form of a salt. There's lots of different options that would work. Really, any negative ion is going to function here, like chloride, NH4Cl. You could have also chosen ammonium bromide, ammonium iodide, ammonium nitrate, really any negative ion that is also the conjugate base of a strong acid, which is going to ensure that the negative ion isn't interacting with the solution in any way. But we can just simplify and say, let's go with NH4Cl as the salt. The other thing we don't know about the weak acid is the concentration that it's going to have. We were told that the base is 0.0025 m, but we weren't told the molarity that my weak acid would be in order to achieve this pH of 9.25. To come up with that, you could imagine our buffer pH equation, technically called Henderson-Hasselbalch, where pH equals pKa plus the log of the base molarity over the acid molarity. In this case, that means NH3, the base is on top, and the NH4 plus, the acid, is going to be on the bottom. And in this case, we're just kind of envisioning how would I get an exact pH of 9.25. Now, the pKa, I can just look up. If you didn't know that, you can just really Google any Ka you ever want, or if you're answering a question, the question you're trying to answer would probably give you that Ka. In this case, I looked it up and found that the Ka of NH4 plus is 5.6 times 10 to the minus 10. So I know that as like a known value, a constant value essentially, and we're going to add that to the log of this ratio. Again, that is the base molarity over the acid molarity, so NH3 over NH4 plus. If you do this math and you find the negative log of 5.6 times 10 to the minus 10, you should notice something interesting. So my pH is 9.25. This negative log is also exactly 9.25, which means if the pKa itself is the pH I'm trying to achieve, then what I really need is this whole term, this log of the ratio of base to acid term. I need that whole thing to be 0, right? Because I want this expression, 9.25 plus 0, it has to equal a pH of 9.25. So I know that that has to be 0. And that is how I can figure out what these molarities have to be. A little bit of extra information that you may or may not know. Let's write this a little bit of a different way. The way you're going to get a 0 when taking the log of something is to have the thing you're taking the log of as a value of 1. The log of the number 1 is 0. So that's what I really need, is I need that ratio of base to acid to simply be 1. And since I know the ammonia concentration is 0.0025, let's fill that out. 0.0025. The only way for this to be a value of 1 is if my acid concentration is the exact same value, 0.0025. Now I know not only that I need to add NH4+, I need to add NH4+ at a concentration of 0.0025. That's going to give me this exact pH of 9.25. So let's neaten that up a little bit and make some space for the second part of this table, which is the function of this buffer. Exactly how does it work? In this particular scenario, the table suggests that we are adding HNO3, nitric acid, to the buffer. Now HNO3 is a strong acid that's going to completely dissociate into H3O+ and NO3-. And the NO3- I don't care about. It's not going to affect the pH, but H3O+ that it brings in certainly will affect the pH of a solution, and that's exactly how the buffer is going to function. Those H3O+ that are coming from the HNO3 are going to react with one of the two buffer components. And that's what you have to choose when you're writing, whatever this neutralization reaction is. My buffer has two things. It's got NH4+, the acid, and it's got NH3, the base. What is H3O+ going to react with? And since H3O+ is an acid, of course, it will react with the base. In this case, in this buffer, the base is NH3. From here, it's just a simple proton transfer, so the H+ leaves the acid, goes to the base, and you can see that what happens here, what keeps the pH from changing, is that the H3O+ from the HNO3 is safely converted into H2O, which means it's not going to drastically lower the pH. My NH3 will turn into some NH4+, so we are going to be producing NH4+, which is a weak acid, so the pH is going to drop a little bit. The point is, we're getting a weak acid here, which is not going to be affecting the pH as drastically as the H3O+ will. How does this keep the buffer, or how does this buffer keep the pH from changing? This is just like a sort of a written description of what you're seeing here in this equation. So you would start by saying that the H3O+ from the HNO3 is converted to water when it reacts with the NH3, the basic component of the buffer. So that's what this buffer is made of in terms of components, and that's how it will function, at least when HNO3 is added. Thanks a lot for watching.